Look at one more problem with strong induction that involves Fibonacci numbers. So the problem here is f of 0, meaning the 0th Fibonacci number, times f of 1 plus f of 1 times f of 2 plus all the way up to f of 2n minus 1 times f of 2n is equal to f of 2n square. And this is for all n that happen to be greater or equal to 1. Okay, so you want to show that for all n that happens to be greater or equal to 1, the following expression holds true. And what you do know is that these f's that I'm talking about here are the Fibonacci number. So what is the statement here? The proposition statement here is, which is P of n is the statement that the entire expression f of 0 times f of 1 plus f of 1 times f of 2 plus going up to f of 2n minus 1 times f of 2n equals to f of 2n squared. Okay, so everything over here is kind of restating the entire problem, and this is the key. You have to state your proposition. You cannot let the reader or the instructor or the TA assume your proposition. You have to state this clearly. After you've stated your proposition, you're not going to solve this for your bases. So the bases over here is I'm looking at for n being the smallest n that I have here happens to be n equal to 1. So I'm going to plug in 1, n as being 1, and for n being equal to 1, the statement that I get back over here is f of 0 times f of 1 plus so everything on the left hand side is going to be f of 1 times f of 2 is equal to f of 2 squared. Okay, and so this is the entire expression here. And again, what are Fibonacci numbers? Well, Fibonacci numbers are defined as f of 0 is equal to 0, f of 1 is equal to 1, and then I'm going to use recursion to define f of n, which is f of n minus 1 plus f of n minus 2, where all n happen to be greater or equal to 2. Okay, so here is the definition that I'm using. So which means that going back to this expression here, I can see that f of 0 is actually 0 on the left hand side times f of 1, which is 1, plus f of 1 happens to be 1 times f of 2, which happens to be 1, equal to the right hand side f of 2, 1 square. This entire piece over becomes 1 equals to 1, and you can see that your basis has been proved. Okay, now you're going to use your inductive hypothesis. Let's assume you're just using the typical. We can just make it even strong. We can even assume that this is a strong mathematical induction. So we're going to assume over here. So let's assume that P of k is true. Okay, so P of k is true. What does it mean that P of k is true? So if I go back to my proposition and I plug in for n being k, P of k is equal to f of 0 times f of 1 plus f of 1 times f of 2 plus going up to f of 2k minus 1 times f of 2k equals to f of 2k squared. Okay, here's the statement that I'm saying. Let's assume this is true. Okay, with that assumption as actually true, what is it I want to show you? What I want to now show, let's show that P of k plus 1 is also true. This is what I want to show you. Okay, so what does it really mean? What is it that I want to show you? Well, if I go back to my proposition P of n and replace n with k plus 1, that'll imply that what I have here is f of 0 of f of 1 plus f of 1 of f of 2 times f of 2 plus going up to I'm just replacing wherever I see n with a k plus 1. So when I do that, this is going to be f of 2k times f of 2k plus 1 plus f of 2k plus 1 times f of 2k plus 2 equals to f of 2k plus 2 square. Okay, so all I've done here is I've just went to my proposition P of n, replace n with k plus 1, and this is the entire green expression that follows over here. Okay, so what can I do on this piece? What can I do on this entire piece in yellow so that I can move from that piece into this green expression? Okay, so one thing I can do here is I'm just going to erase my definition of my Fibonacci numbers just to get some space, and what I'll do is starting with this piece again, starting with this entire piece over here, which is p of k. So let's just write it. Let's just write it down. So this is what p of k is. F of 0 times f of 1 plus f of 1 times f of 2 plus all the way up to f of 2k minus 1 times f of 2k. This is what p of k is. Now on this expression that happens to be p of k, what would I add to it? What would I add to it so that the left-hand side of this expression will be exactly identical to the left-hand side of the green expression? So if I look at this expression in pink that I have here, I've got f of 0 times f of 1, which is this piece over here, f of 1 times f of 2, or the rest piece over there, plus going up to f of 2k minus 1 times f of 2k. So f of 2k minus 1, f of 2k minus 1 is going to be somewhere over here, f of 2k minus 1 somewhere over here, times f of 2k. Okay, something over here is going to be f of 2k minus 1 times f of 2k. Okay, plus everything over in green. So what it tells you is that this expression in pink that I have here, which is p of k, is everything up to this piece in green. Okay, and now on this pink, if I were to add this term and this term over here, then everything in pink will be equal to the left hand side of the green expression. Okay, so let's do that. Let's take everything in pink over here, and what I'm going to do is I'm just going to add to this. Okay, on the left hand side I'm going to add to this f of 2k of f of 2k plus 1, which is this piece over here, plus f of 2k plus 1 f of 2k plus 2 equal to, well, this p of k was equal to f of 2k square. So this is coming back f of 2k square. And because I added everything in yellow over here to the left hand side, I must balance it off. So I'm going to add everything back on the right hand side, which is going to be the same thing, f of 2k plus 1 plus f of 2k plus 1 of f of 2k plus 2. Now you can see that what I have over here, this entire piece in green, which is this piece and this piece, everything green is now equal to p of k plus 1. And if I can show you the right hand side of this expression is equal to f of 2k plus 2 square. If it's equal to this piece over here, then I've proven using my using my strong mathematical induction that this is true for all k. Okay, so now how do I get I've got the left hand side. I've got the left hand side balanced with the left hand side over here. Now I need to look at my right hand side. So on my right hand side, I can look at f of 2k square, and I can look at f of 2k times f of 2k plus 1, and I can see that f of 2k is common. Okay, so just to create some space here, I'm going to erase things that I don't need. So let's get rid of this piece over here, and let's look at these two terms over here. By looking at those two terms, I can take f of 2k out as common, which means what remains inside is f of 2k plus f of 2k plus 1 plus everything over here that remains, which is f of 2k plus 1 times f of 2k plus 2. Okay, now what is f of 2k plus f of 2k plus 1? Well, as per the Fibonacci numbers, as per the binary recursion of Fibonacci numbers, if I take the 2k plus 1 Fibonacci number and add it to the 2k Fibonacci number, what that gives me is f of 2k plus 2 Fibonacci number. Okay, and this piece that remains over here, f of 2k plus 1 times f of 2k plus 2. Now what's common here? Well, what's common here is the 2k plus 2 Fibonacci number, which is f of 2k plus 2, and I can take f of 2k plus 2 out as common. What remains inside is f of 2k times plus f of 2k plus 1. And again, applying the Fibonacci number on f of 2k plus f of 2k plus 1, that gives you f of 2k plus 2 times f of 2k plus 2. That's outside the bracket here. And when I multiply these two guys together, I get back f square of 2k plus 2. And here, this right hand side, which is equal to this entire piece over here, is equal to what I wanted to show you of p of k plus 1. And by doing this, I've now shown you that this is going to be true for all k, because I've shown you it's true for my bases, and I've also shown you it's true for my argument of everything being true up to p of k, which implies that p of k plus 1 is also going to be true.